Okay, good morning. It's not morning, good afternoon. What did we do in the last lecture? We introduced type classes, and type classes look like this. So we had this example. We had the class EQ. And the idea is that such a type class is a set of classes, is a set of types containing certain functions. So if a type A is a member of the type class EQ, then this class declaration tells us that there are certain functions that we can rely on. So there's a function for equality, and there's a function for non-equality, and we give their types. So whenever A is from this type class EQ, then we know there's an equality function that goes from A to bool, and also a corresponding non-equality function. And in such a class declaration, we can also give some default implementations. For example, we can say that non-equality is defined as follows. This is not x equals y, but probably we don't give a default implementation for equality. And then if we have a concrete type, which is member of EQ, then we can override these implementations. So we can give a implementation for equality. We can also give a new implementation for non-equality. And if we give no implementation, then Haskell will take this default implementation. So how does the grammar for these class declarations look like? Well, these class declarations, they are only allowed on top level. So you cannot use them in local declarations. So those things that come after a where or a let, you can only use them on the top level of the program. And then the class declarations look like this. They start with the keyword class, and then comes the name of this type class. And syntactically, this looks like a type constructor. So it's, again, a string starting with a capital symbol. In our example, it's EQ. Then we have a type variable. And, well, this says that if A is a member, if this variable is a member of this type class, then we have all these functions available for the type A. So after this class, the type constructor and the variable, there may be the keyword where, and then a number of declarations. And these C declarations, they are like ordinary declarations, but there are some restrictions, and we will see these restrictions in a minute. Now, how can we declare that some type is an instance of such a class? Well, this is done by an instance declaration. So we can say instance. For example, int is an instance of the type class EQ. And now we can override these default implementations of equality and non-equality. And, well, so then we might have, again, a where clause. And now we can say how x equals y is defined. So in general, the grammar rule for instance declarations looks like this. We start with the keyword instance. Then we have the name of the type class. And then we have some type, and we want to say that this type is a member of this type class. And then we have the keyword where, and now we can override functions that were defined in the class declarations. And here we are also restricted. We cannot use arbitrary declarations, only, well, this non-terminal idecl stands for declarations that are allowed in instance declarations. So what's the grammar rule for cdecl and idecl? Well, the grammar rule is as follows. So the declarations in these class declarations, here we may have type declarations, we may have function declarations, we may declare infix symbols. The only restrictions are here when we declare patterns. So we may only have pattern declarations with a single variable on the left-hand side. So in here we may have something like, well, we declare that z is a constant, which looks like this. So a pattern declaration with a variable on the left-hand side is allowed, but something like this. This is a pattern declaration with z1 and z2, where a whole tuple of patterns is declared at once. Something like this is not allowed in these class declarations. And the main reason is that, I mean, normally if you have patterns, then pattern matching can succeed or fail. And we don't want to deal with the problems that we have if a pattern does not match. So in these pattern declarations, we only allow patterns that match everything, and variables match everything. So these kinds of pattern declarations are not allowed in these class declarations, and normally they are allowed, but not in class declarations. And in instance declarations, the restrictions are even harder. Here one only allows function declarations and these restricted pattern declarations, but no type declarations and no infix declarations. However, this is not very important, and if you forget it, well, Haskell will complain. If you use too complicated declarations, then you have to replace them by a bit simpler declarations. And what types can be declared to be member of a type class? Well, in this example, I said that int is a member of EQ. And indeed, you can do this all types that are built in the following way. A type constructor applied to pairwise different variables. These forms of types, they can be declared to be member of a type class. And this works for user-defined type constructors and also for predefined type constructors. So also for the list type constructor, the arrow, and the tuple type. So let's look at some more examples. I mean, here I said that int is a member of EQ. Now, of course, many types have objects that I can compare for equality. And in the last lecture, I added another instance declaration which stated that if A is a member of EQ, then list of A is also a member of EQ. So I also had something like this. I said if A is a member of EQ, then also list A is a member of EQ. And then there was a definition telling us how to compare lists for equality. So this is probably true. And there are some other cases where it's not true. And, well, this here is called a context. So whenever I have a type, I can restrict it by such a context. And this context means that the type variable A cannot be instantiated by arbitrary types anymore, but just by types from this type class. And these contexts can be used, well, they can be used in normal type declarations, but they can also be used in instance declarations. And in fact, they can also be used in class declarations. So we have to extend this grammar again, because we can now use these contexts. For example, we can use them here, but we can use them also here and at many other places. So the grammar rule has to be extended by these contexts. So what is a context? Well, a context is something like this. So the context just says that a variable has to be member of a certain type class. And in fact, you may have many of these constraints. So variable 1 might be from type class 1, variable 2 has to be from type class 2, and variable n has to be from type class n. Now you can use these contexts everywhere. So for example, if we want to say that some variables have a certain type, we can restrict the type variables in this type by adding such a context. So we can do this in type declarations, but we can also do this when we declare new data types, when we declare new type classes, and when we define new instance declarations. So here in this example, I used such a context in the instance declaration. And to give you an example where we have a context where we restrict several type variables at once, let's write down another instance declaration. For example, I mean, here I said we can compare integers for equality. And I said we can compare lists for equality provided that we can compare the elements in these lists for equality. Now what about tuples? Can I also say that I can compare, for example, tuples of two components for equality? Should a type like this also be member of EQ? Well, how would I compare tuples for equality? I would check whether the first components are equal. I would check whether the second components are equal. So this only makes sense if A is in the type class EQ and B is in the type class EQ. So I should add a context here. And the context should say that A is in EQ and B is in EQ. So now we have this more complicated context, which restricts the instantiation of type variable A, and it restricts the instantiation of type variable B. So if A is in EQ and B is in EQ, then the type of tuples, where the first component is from A and the second from B, is also in EQ. And how would I implement equality here? Well, a tuple xy is equal to a tuple x prime y prime if the x's are equal and the y's are equal. So this holds if x is equal to x prime and y is equal to y prime. So I define equality on tuples using equality on type A and equality on type B. So this looks like a recursive call, but it is not a recursive call, because we have this ad hoc polymorphism, and this equality is the equality on tuples, but this is the equality on type A, and this is the equality on type B. So this is really overloading, as you may know it from object-oriented languages. Depending on the types of the arguments, Haskell chooses the right implementation of the function. Okay? So we have seen that it can make sense to have these contexts in instance declarations. Maybe one more example. I also mentioned the type class show. So there's also a predefined type class show. And show contains all those types where terms of the type or objects of that type can be converted to strings. So if A is a member of the type class show, then there is a function to convert objects of type A to strings. And this function is called show with small s. So there is a function show which maps values of type A to strings. And there are some more functions. And this function show is in fact called by the Haskell interpreter or the Haskell compiler. So whenever Haskell wants to print something on the screen, then Haskell calls this function. So this is like toString in imperative languages. So if you know Java, for example, there is a function toString, which is the analogon to this show function. Whenever you print something on the screen in Java, Java calls toString. And hopefully this function is overloaded and does the right thing for your data type. And well, the same idea is used here. So this is like toString in Java. But it only works for types that are members of the type class show. So if I define my own type, then at first it is not member of the type class show. So let's define my own type. Let's say I define list myself. So I say, OK, I want to introduce a new type constructor list, which takes a type and gives me a new type, namely lists with elements of type A. And list has two constructors, one for the empty list and one for the non-empty list. So let's say nil is the one for the empty list, and cons is the one for the non-empty list. And in this syntax, I have to specify the arguments of these data constructors. So nil gets no data constructor, which means that nil just returns a list A. Cons gets two arguments. The first argument is of type A, and the second argument is of type list A. So in other words, this stands for list insertion. It takes the first element, it takes the remaining list, and it represents the list where, well, this is the first element, and this is the list of the remaining elements. And now if I have some object of type list A, I would like to print it on the screen. Now, if I just define it like this, and I write an algorithm on my list data type, and then Haskell wants to print it on the screen, then Haskell notices that it wants to call show from my list object, but list A is not a member of show. So there's a type error, and Haskell throws some error message. So how can I make it an instance of the class show? Well, there are two possibilities. Either I do it the easy way and I say, I write this here, and this means this should also be an instance of show, but I am too lazy to write the implementation of the show function myself, and I let Haskell do it for me, and then Haskell uses some default implementation of show, which looks more or less useful. But what it will do then, it will print lists using cons and nil, and this looks, of course, a bit ugly. If I want to have my lists being printed in a pretty way so that they look like the predefined lists, then I have to implement this show function myself. And of course, I can do this. So let's not write deriving show, but let's implement this myself. So I will implement this myself now. I will say that my new list data structure should also be an instance of show. So I will now say list A is also an instance of show. Now, of course, this will only work if A is also an instance of show, because I have to print the elements of my list somehow. So if A was an instance of show, then list A is also an instance of show. And how do I want my lists to be printed on the screen? So I now want to implement the show function myself. So I want to implement a function that converts lists of my data structure to strings. And well, if I want to make them look like predefined strings, I could define this myself. I could say, well, I convert this term, which stands for the empty list, I convert this to this string consisting of the opening and the closing square bracket. And if I have a list which is not empty, so something like this, cons x axis, then I want this printed with a colon notation, for example. I could also convert this into something with opening and closing square brackets and commas between, but that's, well, a little bit more complicated, but also not very complicated. So what I will do is I will print x first. So I call show x. Then I want to print a colon. So I print a colon, maybe with some space between. And then I call show x's. And recall, strings are just lists of characters. So this is append, this is list concatenation. So in this way, I can concatenate two strings. So I now concatenate the string for x with the string colon and with the string for x's. And if I have this, then if I now, in my interpreter, if I give in something like cons 1, cons 2 nil, if I have cons 1, cons 2 nil, if I write this in my interpreter and I press return, then what I will get is the following string. Well, it will call show for the integer 1, and this will be converted into the string 1. Then it will print a colon, and then it will call show recursively on this list here. So to do this, it will call show on 2, which gives 2, and a colon, and then show is called recursively on nil, and well, show on nil gives me this. So this would now be printed in this form. And this looks like predefined lists. And if I spend some more effort, I could also write a show function which would convert this into the string opening square bracket 1, 2, closing square bracket. That's doable. So, I mean, we discussed about the ugly way that these user-defined data structures look like. But now we see that if we implement the show function appropriately, they can be printed in a nice way. And then the user will not notice anymore whether these are user-defined data structures or predefined data structures. If you pretty print them nicely enough, they can look nice as well. So this is another example for these type classes. Now we've seen that these contexts can be used in instance declarations, but in fact they can also be used in class declarations. So I can also add a context here. Why would I want to do that? Well, I would want to do that because these type classes can be organized in a hierarchical way. So, I mean, you know this context, this concept of subclasses and superclasses from object-oriented programming. You can do a little bit like this as well in Haskell. So we have some kind of hierarchical organization of type classes. So, for example, let me introduce one more predefined type class. There's a type class ort. So there's a type class ort. And the idea is that ort should contain all those types where you can order the elements. So these are types where you have operations like greater and smaller and greater equal and smaller equal and stuff like this. So you can compare whether one object is greater than another. So here we have operations like greater and smaller and greater equal and also smaller equal. And they all have the type, well, we take one object of type A, another object of type A, and we get back a Boolean. And clearly you can compare integers. You can also compare floating point numbers. That makes sense as well. But strings, yeah, okay, you could define this for strings as well. But lists, that's not so clear. So it makes sense for certain data types, and it makes no sense for other data types. Now, if you think of this, now we have this type class ort, and we have this type class EQ. And somehow they seem to be related, because these are the types where I can compare objects for equality, and these are the types where I can compare objects in such a way that I can decide whether one object is greater than another object. So they should stand in some relation. What should be the relation between these two type classes? Yes?
The ort class must contain the equal class because you can build the equal with a greater equal and smaller equal.
The ort class should contain the equal class. So like this? I think there could be elements which you can easily check for equality, but where it's not so clear whether one object is greater than the other. I mean, think of lists. You can clearly check whether two lists are equal, but whether one list is greater than the other list is probably not so clear. So I think it should be just the other way around, because if you can compare two things if you have these operations, well, then it's very easy to define equality, because x is equal to y if it's both greater equal and smaller equal. So if you have these two operations, you also have equality. But vice versa, I think it's not so easy. So I would say it's just the converse. So if you have greater equal and smaller equal, then you also have equal, but not vice versa. So in that sense, a type should only be in ort if it is also in EQ, but not vice versa. So there can be types that are here but not there. But if a type is here, it should also be there. And to enforce this, I can add a context here, and I can say if A is in EQ, then A could also be in ort. But this means that a type can only be in ort if before I made sure that the type is in EQ. So instance of ort, and then here I have some type, is now only possible if this type is also an instance of EQ. And so by using these contexts in these class declarations, you can organize these classes in a hierarchical way. And now, of course, we can give some definitions here. So we can, for example, say that x is smaller than y. How is this defined? Well, we define this using less or equal. So this holds if x is less than or equal to y, and moreover, they are not equal. And now I'm sure that I can use this. I mean, this is a function that exists for all types from EQ. And due to this context, I can be sure that A is in EQ. So for the type A, this function exists, so there's no problem with calling it here. And, well, maybe I have some more implementations. So this shows that it can make sense to have contexts in these class declarations, because in this way I can organize these type classes in a hierarchical way. And I will, in the end, introduce one more predefined type class, namely the type class num for numbers. So there is also a type class num. And, well, these are the types where we have operations like plus and minus and multiplication and so on. And, well, these operations like plus and minus and so on, they make sense for integers, but they also make sense for floating point numbers. And in Haskell, there's also a data type for fractions, and they make sense there as well. So here we have operations like, well, plus, minus, multiplication, and so on. And if we want to organize this in a hierarchical way, what should we require for A? So this num should again be a subclass of some other existing classes. And which ones are appropriate? Well, one subclass is EQ. So this makes sure that I can compare all numbers for equality. And the other subclass is show. And this ensures that I can print all numbers. So num is a subclass of EQ and show, but not of ort, because maybe for some numbers it's not clear how to order them. So this is how it's predefined in Haskell. And all the numbers that we've written up to now, they are in fact from types that are members of the type class num. So if in Haskell you want to find out what is the type of a number like 1. Up to now, we've always said that the type of 1 is int. But, well, in fact, you can use this to, for example, to add it with another integer. But you can also use this to add this with another floating point number. So, I mean, in Haskell, you can write something like this. But it's also fine to write something like this. And so how does that really work in Haskell? What is the type of 1, what is the type of 2, and what is the type of plus? And, well, if you just write 1, then it's not so clear whether you meant 1 as an integer, or whether you meant 1 as a floating point number, or as a double, or, well, there are several numerical data types in Haskell. And so, in fact, the type of 1, the most general type of 1 is something else. It's an arbitrary type. So because we don't know, it could be int, it could be float, it could be double. But it's not completely arbitrary. It must be from the type class num. It's an arbitrary type which is a member of num. So it's A, but A is restricted to a type from the type class num. So this, in fact, is the type of 1. And since int is a member of num, and float is a member of num, and double is a member of num, you can use 1 whenever at positions where you need an integer. You can use 1 at positions where you need a double. This is all possible. And, well, the type of plus then obviously is A to A to A. And a could be int, or a could be double, or a could be float. But a cannot be bool. So a can be any data type from num. And now you see that this is OK, but this is also OK. So you can now add two numbers, even if one number is an integer and the other number is a floating point number. This works fine, because in the end they are both, because there's the type, a hierarchical organization of type classes which makes sure that this works in the desired way. And so if we wrote 1 has type int, well, that's one possibility, but in fact the most general type of 1 is this and not int. But this we can only understand if we know what type classes are. So this is the concept of type classes. And well, what you have to keep in mind is these type classes allow you to overload functions. I mean, we overload functions like plus, or like equality, or like greater, or like smaller. And depending on the types of the arguments, the right implementation is chosen. So the concept is like in object orientation, but of course the realization is a little bit different in Haskell. But it's not a completely new idea. You may know this from imperative languages as well. OK, so this ends more or less the introduction of the concepts of Haskell. So now you know, well, you know not everything, not all concepts from Haskell, but you know a lot of them. And this more or less suffices for the rest of the lecture. So what we'll do in the next lectures is discuss a bit about programming techniques. How can you use a functional language like Haskell for certain programming techniques, in particular program techniques that are specific to functional programming and which you don't have in imperative programming. And then afterwards we will look at the theory behind functional languages. And we will always look at Haskell as an example of a functional language, but now you know enough Haskell to understand the rest of the lecture. OK, so let's now move on to specific programming techniques that are used in languages like Haskell. And we will focus on 3 specific techniques, namely the use of higher order functions, the use of lazy evaluation, and the use of monads. And the second subsection of this chapter is higher order functions. OK, so what are higher order functions? A higher order function is a function that takes a function as argument or returns a function as its result. So it's a function where the argument or the result is again a function. So a function whose argument or whose result, or maybe both, is again a function. So did we already see these kinds of higher order functions? Well, one of the easiest functions that we looked at the very beginning was a function like this, square from int to int, which takes an integer and returns an integer. Is this a higher order function? No. I mean, the argument is of type int. That's not a function. The result is of type int. That's also not a function. So this is not a higher order function. And functions that are not higher order functions are called first order functions. But we also had a function plus. And we wrote this in the curried form. So we wrote this in this form. It goes from int to int to int. And this function arrow implicitly associates to the right. So this means that. Is this a higher order function? Yes, it's a higher order function. The argument is an integer, so that's not a function. But the result is a function. So the result is a function. So indeed, this is already a higher order function. Because if I write +1, then, well, the result of this is a function. It's a function from int to int, which takes a number and increases it by 1. So indeed, we have already seen higher order functions, but we've only seen functions where the result is a function. We haven't yet seen functions where the argument is a function. Now that sounds rather obscure, but in fact from everyday mathematics we are used to such higher order functions where also the arguments are functions themselves. And one very natural higher order function where the argument is a function, which you know from mathematics, is function composition. So you all know the concept of function composition from mathematics. What is function composition? Well, if you have a function f and a function g, you can write this circle in between. And this means this is the composed function which you get by first applying g and then applying f. So this circle operator obviously takes two functions as arguments. It takes function g and function f, and it returns another function, namely this composed function. So this takes two functions as arguments, and it also has a function as a result. And well, of course, function composition we can also define in Haskell. So let's define this function composition operator ourselves. And let's do this as an infix function. So let me define, well, since I don't have a circle on the keyboard, we do this with a dot. So dot should be the function composition operation. So how can I define this in Haskell? Well, if f is a function and g is a function, then f composed with g should be the following function. It should take an argument x, so lambda x is the function which takes an x and returns, well, what does it return? It first applies g to x and then applies f to the result. So it first applies g to x and then it applies f to it. So this is easy to define in Haskell. Now, what's the type of this? Well, both f and g are functions. So f is a function, g is a function, and the result is also a function. And now I have to come up with the correct types. So we first apply g to the thing. Let's say this has type A. Then g must take an argument of type A and map it to an arbitrary argument of type B. So let's say g has the type A to B. So then this thing has type B. And to make this well typed, f has to operate on the stuff that g produced. So the argument type of f must be the same as the result type of g. So f must go from b to something else. Well, to keep it as general as possible, let's say f goes from b to c. And then what does the resulting thing have? What is the type of f dot g? Well, it's a function that takes an element of type A and returns this thing here. And this thing has type C. So the resulting thing goes from A to C. And this dot is an infix function. So let's declare this as an infix function. Let's say it associates to the right. It doesn't really matter because function composition is associative. So if you want to associate to the left, that's also fine. And we have, I will give this very high binding priority. And in fact, this is predefined like this. So this is the predefined function composition in Haskell. So indeed, this dot operation is function composition in Haskell, and it's predefined like this. So this is predefined in Haskell. So we can see that this is a very natural higher order function where the arguments are functions and the result is also a function. To illustrate this, let's suppose we have a function half and a function square, two, well, half and square numbers. So if we have this half composed with square and we apply this to a number, then what will happen? What will be the result? Well, this is the function that first squares its argument and then halves it. If we square 4, we get 16, and if we compute the half of 16, this is 8, I think. So, well, half and square we have to define ourselves, but one more. So if we have this, so I can also define functions by lambda expressions like this. So what's this? 17, right. That's the function that first squares its argument and then adds 1. Okay. Okay, so this was meant to introduce the concept of higher order functions. Now, what are they good for? Is this just a toy, or is this useful for something? Well, this is useful for something because the main programming technique with higher order functions is the following. It's the idea that you try to identify typical structures of algorithms. So there are many algorithms that essentially operate in the same way. And instead of implementing all these algorithms separately, it would be a good idea to identify the similarity and implement this recursion structure once and for all by a suitable higher order function. And then you can reuse this higher order function whenever you need an algorithm that works in a similar way. So that's the programming technique. So the programming technique that I want to illustrate to you in the rest of the lecture today is identify typical structures of algorithms And so if we have many algorithms that operate in a similar way, let's try to abstract from the minor differences between these algorithms and implement the main thing, the main similarity, using a suitable higher order function. And implement this general structure by a suitable higher order function. By a suitable higher order function. And then in actual algorithms, which would work according to this general structure, reuse this higher order function. So reuse these higher order functions whenever possible in actual algorithms. These higher order functions in actual algorithms. And the advantage is, well, since the main effort of the algorithm is in this higher order function, you can reuse this all the time, so your programs tend to get very small and very easy to understand by other people because, well, if these are very general structures, then other people know this structure as well, and they will immediately understand your code because they see, aha, this is this well-known pattern, which is reused here again, and so they immediately understand what your program does. So small and easy to understand programs. Okay, and I will try to illustrate this to you with several examples. Okay, so maybe the easiest of these higher order functions that implement such a general pattern is the function map. So the function map. Okay, so as I said, try to identify typical structures of algorithms. So let's write some algorithms and see whether we can identify some similarity between them. So the examples that I want to show you are the following ones. I want to implement a function suck list, and what it should do is the following. It should traverse a list. Well, this is dirty. It should traverse a list and increase every element in the list. So that's the task. It's not too difficult, but it's difficult to read, but not difficult to understand, I hope. So this function suck that I use there is just meant to increase numbers by 1. So this function suck on the transparency, that's a function, let's say, from int to int, which is just increasing numbers by 1. So it's just plus 1. So what does suck list do? Let's try to understand what suck list does. If I call suck list with some list of numbers, so some list x1 to xn, then what does it do? Well, if the list is empty, it returns the empty list, and otherwise it applies the function suck to the first element and calls itself recursively. So it will apply the function suck to the first element of this list, and then it will call itself recursively. And so the second element of the list will be suck of x2, suck of x3, and so on, and in the end it will be suck of xn. Okay. So what's the general idea of this algorithm? It traverses the list and applies the function suck to every element of the list. Okay. Now let's look at a completely different algorithm that does something completely different, namely the function square root list. Now the function square root list is completely different from suck list because suck list operates on lists of integers, but square root list operates on lists of floating point numbers. What does it do? Well, if the list is empty, it returns the empty list, and otherwise it applies the square root function, which is predefined, to the first element and then calls itself recursively. So if I apply square root list to a list like this, then I apply square root to the first argument, I apply square root to the second argument, and in the end I apply square root to the last argument. Now, if I look at these two algorithms very closely, then I might realize that they are somehow similar. I mean, I hope you realize this. So this is really very similar. I mean, the concept, how these algorithms operate is identical. Traverse a list and apply a function to every argument. There are some differences. So there are, in fact, two main differences. One difference is that, well, this operates on lists of integers and this operates on lists of floating point numbers. So that's one difference. And the other difference is this applies the function suck, whereas this applies the function square root. And that's it. These are the only differences between these two functions. So it would be very nice if I wouldn't have to implement such functions from scratch every time I need that. But if I could identify this general pattern which says that traverse a list and apply a function to every element. I mean, that's a general pattern, and I will now try to abstract from the differences and implement this general pattern once and for all. So abstract from their differences. So what are the differences? Well, one difference is the type of the elements of the lists. So we have to replace the type of the elements, int in the first case and float in the second case. And if I want to abstract from this, well, abstraction essentially means I replace all those things that were different in one, and in the other function I replace this by variables. So I will replace int or float by a variable, a type variable. By a type variable A. And of course, I can only do this if I have a programming language that has parametric polymorphism, so a language where I have type variables. But Haskell has type variables, so that's fine. So here I need parametric polymorphism. And the other difference is in the one function I apply suc, in the other I apply square root. So let's replace this by a variable. Replace suc, respectively square root, by a variable, by some variable g. And of course, this g is a variable that stands for an arbitrary function. So I have variables of function type, and that's only possible in languages that allow higher order functions. So here I need a language that allows higher order functions, but Haskell allows that. And then, so what do I want? I want a function, a general function f, and if I apply f to a list x1 to xn, then it should not give me suc x1 to suc xn and not square root x1 to square root xn, but it should give me gx1 to gxn, and g can be an arbitrary function. So if I want this, then how would the implementation of f look like? Well, the implementation of f would look like the implementation of suc list and square root list. So instead of suc list or square root list, I write f. So f of the empty list is the empty list, and f of x colon x's is, well, it's not suc x, it's not square root x, it's g of x. So g can be anything. And then f is called recursively on the rest of the list. And what would be the type of f? Well, I will now not operate on lists of integers or lists of floating point numbers, but lists of a. I mean, a can be anything. And in fact, I can make this even more general. The elements that I get in the end, they may also have type A, but they may also have some other type B. So in general, I can even allow this. So this looks as general as possible. And now, of course, I have this function g here. And, well, this g should in principle also be an input to my function here. Because what the function f does, of course, depends on g. G could be suc or g could be square root. So g should also be an input argument of f, because only then I can use this g on the right-hand side. So this is not a legal Haskell declaration, because this function g occurs on the right-hand side, but it was not mentioned on the left-hand side here. So let's write it again. Let's now also have this g as one of the arguments here. And then this function is called map. So instead of f, let me write map. But now I have this g as first input argument. Second input argument is the list. And here I have x colon x's, and I have g x. And instead of f, I now write map g. So map g x's. So what does map do? Map takes a function and a list, and it applies this function to every element in the list. So what is the type of map? So the first thing is a function which has some type. Then comes a list with elements of type A. And the result is also a list with elements of type B. So what is the type of G then? A to B, right. So map takes a function which goes from A to B and a list with elements of type A, and it applies this function to every element in the list. So indeed, map G applied to some list x1 to xn is the list where I have g of x1, g of x2, and g of xn. Oh, this is also written on the slide here. Okay, so now I managed to identify the similarities, and I generated this new function map. And as we can see, this is a higher order function because it takes a function as an argument. The first argument here is a function, and then it applies this function to every list element. And now, what is this good for? Well, if I have this function map, then there is no need to implement sucklist and square root list as I did it up to now, but I can reuse this function map because sucklist and square root list are just special cases of map, if you want. So now sucklist and square root list can be implemented in a much shorter way. Because how would I implement sucklist? Well, sucklist is like map, but it's the special case where the function g is suc. So this is just map suc L. That's it. So to implement sucklist, I have to map the function suc to every element of the list L. And this is a one-line definition, so this is pretty short. And square root list L is obviously map square root L. And this is very readable because map is such a common, such a useful function that it is predefined in Haskell. So every functional programmer knows what map is. And if someone reads a definition like this, everybody immediately understands what that does. So it's clear this applies this function to every element in the list. So this is very short. There's no danger that you do any mistake in this implementation. Everyone can understand it.
So if we write it like that, we know that all the function is operate on integer and no.
Yes, that you wouldn't know. If you want that, then you have to add the type declaration as before. So, well, it depends on what suc does. I mean, if suc is defined like this, if suc goes from int to int, then you could automatically infer that it goes from list of integers to list of integers. But yeah, otherwise you have to add the type declaration as before. And you can do this even shorter. So instead of writing it like this, you can also omit this L here and just write this. And that would do the same thing. Sucklist is map suc. Right? So why? Because if I apply sucklist to the list 2, 3, Haskell does outermost evaluation. So it evaluates sucklist to map suc. So I get map suc 2, 3. And this will map suc to 2 and 3, and then in the end I will get 3 and 4 as expected. And this is pretty short. And as you just asked, if you want the type declarations, those you still have to write. Okay, so this is the idea to use higher order functions in order to simplify programming. And there are many of these typical algorithmic structures that you can apply, that you can express by higher order functions. And I mean, here with map, we express the idea, traverse a list and apply a function to every element. Now let's do another example where we have a different recursion structure, but also a very common one. And let's again try to abstract from the differences. And let's try to define a suitable higher order function that computes the general structure of the algorithm. So the next example is the function filter. Okay, the function filter. Let's do this in a similar way. Let's define two functions that look somehow similar, and let's try to extract what they have in common. So here we see the function drop even. And the idea of the function drop even is that we take a list of integers and we drop all the even numbers from this list. So we throw out all the numbers that are even. Right, so if you want to understand what it does, drop even, well, if I take the list 1, 2, 3, 4, and I drop all the numbers that are even, then I drop 2 and 4, and so the only numbers that remain are 1 and 3. So that's the goal. Throw out certain elements. Okay, how does it work? If the list is empty, I return the empty list, and if the list is non-empty, so it starts with some x and then comes some rest list x's, then I check whether x is odd. Odd is predefined in Haskell, and if x is odd, then it may remain in the list. So then I keep this element x. This will be the first element of my result list, and I call drop even on the rest list. And if x is not odd, so if x is even, then it gets dropped, and I call drop even on the rest of the list. So this is understandable, I guess, and well, it does what it should. Now let's look at a completely different function that does something completely different, namely it works on strings. It's a function drop upper. And drop upper works on strings, and it should drop all uppercase letters from a string. So for example, GmbH, that stands for Gesellschaft mit beschränkter Haftung. So for those of you who speak German, this is what is called limited in English. So it's a way to organize companies. Anyway, you don't have to understand this. You have to understand that this is capital and this is capital, and these two are non-capital. That's the only purpose. And drop upper should throw out all uppercase letters. So it throws out capital G, capital H, and MB remains. So this converts companies into megabytes, if you want. So how does the algorithm work? It's a completely different algorithm because it does some string processing. And it uses a predefined function isLower. If you want to run this in Haskell, the function isLower, I mean, Haskell is organized into different modules. So that's like the libraries in Java, for example. And isLower is not in the standard library, so this isLower function is in a special module for operations on characters. Is in a module called character with capital C. And if you want to use functions from other modules, you have to import these modules. So on the beginning of your file, you have to write import character. If you write this in the beginning of your file, you import all functions that are exported from the module character. If you only want to import certain functions, you can write parentheses here and say, I want to import just the function isLower. I don't want to import the rest of it. So if this is omitted, if omitted, then all exported functions from the module character are imported. So this is pretty much the same as import and export of modules in other languages. This is just meant to organize the huge set of predefined functions in a way. So, okay, so isLower is predefined, and if we import the right module, we can use it. And then this function drop upper works as follows. If the list of characters is empty, then it returns the empty list. And otherwise, it checks whether the first element is a lowercase symbol. And if it's a lowercase symbol, the x can be kept, and drop upper is called recursively. And otherwise, this x has to be thrown away, and drop upper is called on the rest of the list. So as you can see, these algorithms do some things that are completely different, but somehow they look similar, I hope. So they both traverse a list, and they check every element. They check for every element, does it satisfy a certain property? Here we check whether the element is odd. Here we check whether the element is a lowercase symbol. If the element satisfies the property, then the element is kept. And if the element does not satisfy the property, then the element is thrown out. So the structure of this algorithm is the same. But there are two differences. One time we operate on lists of integers, the other time we operate on lists of characters. And also the functions that we use for this filtering are different. One time we use odd, and one time we use is lower. And so the idea is, again, let's abstract from the differences, and let's try to come up with a general function that, well, does those things that are similar in both algorithms. Okay. Okay, so the idea is as before. Let's abstract from those things that are different. So abstract from, well, one time it was int, one time it was character. So let's abstract from int or character and replace this by a type variable a. And this, of course, is again only possible if we have a language with parametric polymorphism. And the other thing that is different, well, we use odd in one function and is lower in the other. So let's abstract from odd, respectively from is lower, and replace it by an arbitrary function g. And so if we do that, then we get the following function. Well, let's call it filter. So what does it do? If the list is empty, it returns the empty list. That was the same in both cases. So filtering the empty list gives the empty list. And filtering a non-empty list, where we start with x and then we have x's, well, here we test. Does my element satisfy the condition? And, well, here the condition was odd. There the condition is lower. And in general, the condition is some arbitrary check g. Does this satisfy the condition g? And if yes, x can be kept, and the function is called recursively on the rest of the list. So then we keep the x, and we call this filter recursively on the rest of the list. And otherwise we throw away this x, and we have just filter on the rest of the list. So this is the same as the functions before, but I replaced odd, or is lower, by g. And now, of course, this g is used on the right-hand side. So this g should be an extra argument of filter. So filter should take this filter function g and filter away all elements that do not satisfy g. So what is the type of filter? So filter takes this function g, and it takes a list of arbitrary elements, and it returns a list. Well, the only thing it does is it throws out certain elements from the list. So the type of the elements will not change. So the result type is, again, lists where the elements have type A. And what is the type of G? A to bool, right. A to bool. So I can apply it to elements from the list, and it has to give me true or false. So for every element, either G holds or G does not hold. Right, exactly. So this is filter. And now that I have filter, I can re-implement drop even and drop upper. And now this is, as expected, very easy. Drop even is now just filter odd. So in other words, filter away everything that is not odd. And drop upper is filter is lower. In other words, filter away everything that is not a lowercase symbol. And that's pretty short. Yes?
So wouldn't it be a much better abstraction for filter to take a list of A to bool filters, functions? Because we can only apply one mapping function, but we could apply many filters.
Sure. That would be another possibility to specify a typical form of an algorithm. And, well, you can implement these higher order functions yourself. So call this filter list or filter prime or whatever, and you can implement this easily as a higher order function and use it. So I don't think that this version of filter that you suggested is predefined, but if it's not predefined, just define it yourself and then use it. So this, I mean, those functions that I showed to you as examples, they are so common that they are predefined. But indeed, it makes sense to define such higher order functions yourself. And in particular, I mean, these ideas for these functions like map and filter, they are not only useful for lists and not only for predefined lists, but they are also probably useful for your user-defined data structures. So if you define a data structure for trees, then you can also implement a map function and a filter function for your trees, or you have something for graphs, and that can make sense as well. So functions like map and filter and so on, they very often can also be defined for user-defined data structures, but of course there you have to define them yourself. And for user-defined data types. And, well, some very common functions, in particular for lists, are predefined, like map and filter, but many others are possible as well. So this was great. So since this is so enjoyable, let's do one more example, a last one. Okay, I mean yeah, I know you get bored, but this one is a bit more complicated than the others, so one more. That's the last one. The function fold. Now, to make this easier, I will now illustrate this not with predefined lists, but with my user-defined lists, the ones with cons and nil. And suppose I have the following two functions. And let's see whether we can find similarities between these two algorithms. So I now wrote two algorithms, add and prot. And this time they operate on my user-defined data structure for lists. So what does this do? Add takes a list of integers, and it adds up all elements in the list. So, well, if the list is empty, if it's the nil list, then I get 0. And otherwise, well, if the list looks like this, I use the function plus, and I apply plus to the first argument, and I call add recursively on the rest of the list. So this adds up all elements in the list. Now, prot does something completely different. It multiplies all elements in the list. So this time, if I have the empty list, I get 1. And otherwise, I call times and multiply the first element with the product resulting from the rest of the list. So add adds up all the elements in the list, and prot multiplies them all. So in other words, if I have a list like this, cons x1, cons x2, and so on, cons xn minus 1 and cons xn nil. Then what does add do? Well, you can see if something starts with cons, then add replaces this cons by plus. So if you look at the definition of this, you can see that if you have a cons here, then the cons is replaced by plus. The x remains, and add is called on the rest of the list. And if this starts with cons, then again the cons is replaced by plus, and add is called on the rest of the list. So all the conses are replaced by plus. So I have plus x1 plus x2 plus xn minus 1 and plus xn. And finally, if I arrive at nil, what happens here? Well, at nil is 0. So the nil is replaced by 0. So add replaces cons by plus and nil by 0. What does prod do? If I apply prod to such a list, cons xn minus 1, cons xn nil. Well, if you look at this, we see what happens. Cons is now replaced by times. So instead of cons, I now have times. Here I also have times. Here I also have times. And here I also have times. And what happens with nil? Well, prod of nil is 1. So nil is replaced by 1, not by 0, because multiplication with 0 always gives 0. Okay, and well, somehow these two algorithms look pretty similar, as we can see. What they do is, essentially, they just replace data constructors. The data constructor cons is replaced by plus, and the data constructor nil is replaced by 0 here. And in the other algorithm, cons and nil are replaced by times and 1. So let's try to abstract away from the differences. And well, the difference is, here we take plus, there we take times. So let's take some arbitrary function g. And here we take 0, and there we take 1. So let's take some arbitrary value, e. OK, so we abstract from, from plus and times, from plus respectively from times, and replace this by some function g. And we also abstract from, well, one times we had 0, one times we had 1. So let's replace this by an arbitrary variable. Let's call it e. And so the idea is we replace all occurrences of cons by g and all occurrences of nil by e. So let's write down the definition of the algorithm. And this is called fold. So how does fold look like? If I apply fold to the empty list, so I apply fold to nil, then, well, up to now I had 0 in one case, 1 in the other case, so I want to abstract from this. Now I return e. And if I have a non-empty list, so something like this, cons x-axis, then what do I get? Well, up to now I had plus in one case, times in the other case, so I want to abstract from this, so I take g. And, well, this g, so this plus or times, is applied to x. It's applied to x. And then I call the function recursively. So here I have, well, here I called it add, there I called it prod, now I call it fold. So now fold is called recursively on the rest of the list. So that's the general form of this algorithm. And now, of course, I have this g and this e on the right-hand side. And this g and this e, they are arbitrary, so I should add them as extra arguments to the left-hand side. So let me add them as extra arguments here. So I have g and e. Whenever I have fold, I now add G and E here, here, and here. And that's the definition of fold. Now, what's the type of this? Okay, so I have this function G, which has a certain type. Then I have this E, which also has a certain type. Then I have a list. Well, let's say this is an arbitrary list with elements of type A. And then I have a result. Now, in general, the results can be arbitrary. It doesn't have to be of type A. It can also be of type B. It doesn't really matter. So let's say, in the end, fold takes a list with elements of type A and returns a result of type B. If this is true, then what is the type of E? B. Then E must have type B here, because here this has type B, then therefore this has also type B. So E has type B. And what's the type of G? Let's see. So G is applied to two arguments here. First argument is this X thing, the second argument is this, and it has to yield a result. So this has type A, because this is the first element from my input list. What's the type of this? B. And what's the type of the whole thing? B. Because in the end, fold should return something of type B. So in other words, G takes an element of type A and an element of type B and returns an element of type B. So G goes from A to B to B. So if this is true, then I can now implement add and prot in a more concise way, namely as follows. Add is now just fold. And well, now I have to say, with which function do I want to replace cons? I want to replace cons by plus, and I want to replace nil by 0. And prot is fold, but now I want to replace cons by times, and I want to replace nil by 1. So the idea is fold G, E, axis replaces all data constructors by new functions. G, respectively E. So cons is replaced by G and nil is replaced by E. And well, fold has many applications. Let's look at another example. For example, this function concat. What does this do? So concat takes lists of lists. So it takes a list of lists, and it concatenates all the lists in this list of lists. So if you want to see this with predefined lists, then it looks like this. So concat, if I have a list like this, 1, 2, 3, 4, 5, 6, then concat takes all these lists and appends them. So the resulting list would be the list from 1 to 6. So if I do this on my predefined list, then it looks like this. If my list of lists is empty, well, then the result is the empty list. And otherwise, if my first element list is X, and X is my remaining list of lists, then I get the result list as follows. I call concat on the remaining list of lists, and in the end, I append the first element list in front. Right? So I get the first element list, and I append this to the result of calling concat on the rest of the list. And this, again, follows the same structure as add and prot. So I shouldn't define concat like this, but it's much nicer, much more elegant to define it using fold. So if I define this using fold, how would it look like? So what should be the arguments to fold? But, sorry? Plus nil. Append. Append nil, right. So this means that all occurrences of const have to be replaced by append. And, well, nil has to be replaced by nil. Right, so if I have concat and I had cons x1, blah, 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 and in the end, cons xn nil, I now have this cons replaced by append, and the last cons also replaced by append, and the nil is replaced by nil. So indeed, this just appends all the lists, all the element lists in this list of lists. Yes?
Is there a difference between append and the plus operator?
No, that's the same. It's just that I had my predefined lists here. So, I mean, the predefined plus operator works on the predefined lists of Haskell and not on the data structure list A that I defined myself. But it's the same thing, append and plus. Yeah. If your G function has a different type than that, you get a type error. I mean, you can only apply fold if the type is like this, or if it's less general. So, I mean, you can, of course, instantiate the type variables in any way you like. OK, so on Wednesday, so the day after tomorrow, there will be lecture instead of exercise course. And in fact, this lecture, the first half of the lecture on Wednesday is for everyone. The second half of the lecture is only needed for bachelor students. For the master students, this will not be part of your exam, but you are very welcome to stay for the whole lecture and listen to the rest of it as well. So see you on Wednesday.